in this example, we'll look at the transient response of a capacitor. So let's say we have a capacitor that is 40 microfarads, and at time t equals 0, it has a current of 40 times the rectangle function of t minus 1 over 2 milliamps. So I probably don't even need to say t over 0 because it's 0 everywhere that it's not that rectangle. I find the rectangle function kind of strange, but it is given in your book. And so we need to know something about the initial condition of the capacitor. And this capacitor, we are told, is initially uncharged. And you do need to know the initial condition. So V of 0 equals 0. And our goal is going to be to find V of t, P of t, and W of t. So notice we are looking for functions. We're not looking for the value of the voltage at some particular time, or the energy or the power at some particular time. We're looking for an expression that will show us the power, that will show us the power and the energy at all times. All right. So first let's take a look at what this function looks like. And our axes will be current in milliamps and time. And what this function means is that we have a rectangle that's center is at 1 and its width is 2. So if its center is at 1 and its width is at 2, then it goes from 0 to 2. And during that time, it has the constant value of 40. And at other times, it's 0. So that's what the rectangle function is. So it's 0, and then it becomes 40, and it's 40 for 2 seconds, and then goes back to 0. And it looks like that. So that is what our current function looks like. So let's start by finding the voltage. And we know that V of t equals V naught plus 1 over c times the integral from t naught to t of I dt prime. So our function here has 3 different parts. So we have the part where t is less than 0, and when t is less than 0, I is 0. And we have t between 0 and 1, and there I is 40 milliamps. And we have t greater than 2, this should be 2, t between 0 and 2, and t greater than 2, and I is again 0. Now, notice that our capacitor is changing current instantaneously. That's okay for a capacitor. It can change current instantaneously. It can't change voltage instantaneously. So when we end up with our expression for voltage, we want to check and make sure that the voltage is not changing instantaneously, because if it is, something is wrong. Okay, so it's initially uncharged. So at t less than 0, it's going to be 0 because it's uncharged plus 1 over c times the integral of 0 dt prime. Or that's our voltage. So our voltage is 0. But we need to be careful because that's not always the case, because even if the current is 0, the voltage might not be 0 because of this term right here. So a capacitor can have a voltage even if there's no current. And if you think about it, in steady state conditions, a capacitor will be charged and it'll have a voltage, usually, but it won't have a current, and that's a normal steady state condition. Alright, so now let's look at t between 0 and 2. So I'm doing voltage first, and then we'll go through and do power and energy. So V of t will equal V of 0 plus 1 over c times the integral of 0 to t prime. Now we're putting t prime not 2, because if we put 2, what we'd be finding is the voltage at time 2. We don't want the voltage at time 2, we want an expression for the voltage between times 0 and 2, so we want it for any time t. And actually, let's not put the prime there. We'll put the prime inside here. And so this is going to be, our current at this time is just 40 milliamps. So it'll be 40 dt prime milliamps. And so this was 0. The capacitance was 40 microamps. So that's 1 over 40 times 10 to the negative 6. And the integral of 40 is 40 t prime, using the t prime just to distinguish it from the t as a separate variable. And that's in milli, and that's from 0 to t. And so this answer now will be in millivolts. So this number right there is 25,000 times 40 millivolts. Oh, I forgot my t. There's my t. 40t. Which gives me, if I multiply through by the 10 to the negative 3, if I use the milli there, 25,000 times 40 times 10 to the negative 3 is going to give me 1,000 t for t between 0 and 2. So this is V of t for t between 0 and 2. So now we need to look at t greater than 2. So V of t for t greater than 2 is going to be V at our starting time, which is 2, plus the integral from 0 to t of our current in this time period, which is 0, dt prime. So the integral of 0 is just 0, but V of 2 is not 0. So let's find V of 2. Now, the voltage cannot change instantaneously. So whatever the voltage is according to this function at time t equals 2, it has to be equal to that on this side. So at t equals 2 minus, which means 2 coming at it from the smaller side, V of t equals 1,000 times 2, or 2,000. So now we know V of 2 has to be 2,000. It can't change instantaneously, and so it has to be 2,000 on this side as well. So it's 2,000, And this is in volts, and this is in volts. So 2000 volts. So let's just summarize this, what we got for the voltage. We have V of t equals 0 for t less than 0, 1000 t for t between 0 and 2, and 2000 for t greater than 2. So that's our voltage function. And these are all volts. We're also supposed to find the power, and we know that power equals current. Well, we have expressions for both current and voltage, so this shouldn't be too hard. So let's look at our 3 time intervals. We have t less than 0, t between 0 and 2, and t greater than 2. And we'll put our current and our voltage, and then we'll multiply to find our power. So t less than 0, our current is 0, our voltage is 0, so our power is 0 watts. Between 0 and 2, our current is 4 milliamps. Our voltage is 1000 t volts. So multiplying the 1000 times the milli, those cancel each other out, and so we'll end. And then for t greater than 2, we have the current is 0, and the voltage was 2000. But 0 times 2000 is 0, so our current is 0, our voltage is 2000, and our power is 0. Okay, so how about our energy? So we know that energy is 1/2 CV squared. So for t less than 0, that's going to be 1/2 times c times 0 squared, which is 0 joules. For t between 0 and 2, we'll have 1/2 times our capacitance, and our capacitance was 40 times 10 to the negative 6, so 40 microfarads. And our voltage was 1000 t. And that'll be squared. So 1/2 times 40 times 10 to the negative 6 times 1000 squared, I get to be 20 t squared joules. Now the book that I got this out of had an answer of 20 t squared millijoules, but I checked my work and I didn't see where a milli would be in there. But if someone does, leave me a comment or send me an email. Okay, now for t greater than 2, this is all our energy. W equals W 1/2 times 40 times 10. Our voltage here was 2000 volts squared, and that gets us 80 joules. Again, my answer said millijoules, but I still didn't see where that was. Okay, so that's our example for a capacitor.